Hello, my name is Alejandro Garcia. My partner is Saul Olivo. We are undergraduate students at Texas A&M International University. We would like to start by saying thank you to the National Science Foundation, as well as to our mentor, Dr. Mustafa Al-Lail. Uh, our research is called Machine Learning for Network Intrusion Detection, a comparative study. Network intrusion is a big problem in the world. In fact, according to Forbes magazine, cyber attacks cost U.S. Businesses more than $6.9 billion, and this is only in 2021. So we're developing a machine learning approach to detect attacks before they happen. This is the overview that we will follow for the presentation. First, we will introduce a problem and the goal of the research. Then we'll show some preliminaries like the dataset, algorithms, and techniques that were used in the research. After, we will jump to the related work section, where we will highlight work that has been done before on this topic. Next, we'll showcase our methodology, showing the step-by-step process that was followed, divided in those three sections. Then we will show the results of our study and discuss our comparisons, to finish with a conclusion to summarize our research and our main ideas.
So first, we're gonna go over the introduction. Um, the reason why we had to do a research is to reduce the number of intrusion to the systems. As we know, as the internet progresses, many more attacks develop. So our goal is to reduce the amount of intrusion into the systems. And with those intrusions, there's a consequences that come with it. As for a small business, financial losses are a big issue. Just for a small business, it can range from 55K to a million, depending on the size of it. And data for bigger companies such as Twitter, Facebook, or YouTube, financial losses is just is not as important as a data breach. As we know, in the past month, Twitter had an intrusion that leaked over 4.5 million users' information. It was supposed to sell for just $30,000.
So the main goal of this research is to be able to combat cyber attacks by creating a network intrusion detection system that is able to predict and categorize attacks. To accomplish this, the first task is to resemble real-world traffic by using the CICIDS 2017 dataset, a dataset provided by the Canadian Institute of Cybersecurity. Then implement the machine learning algorithms to be able to classify and predict abnormal activities. Next, we need to evaluate the performance of the algorithms by doing a comparative study. At the end, the last goal is to create a model able to predict and categorize attacks. Now we're going to jump into the preliminaries. The dataset, as I mentioned before, we use the CICIDS 2017 dataset, a dataset provided by the Canadian Institute of Cybersecurity. This dataset contains more than 2.8 million samples, and each of these samples has 79 features, which are used to describe the state of the sample. There are 15 types of attacks in this dataset. This include benign, which represents just normal traffic, normal flow, and 14 more, which are harmful attacks like infiltration or denial of service. A big problem with this dataset, though, is that its tendency to being biased towards benign attacks. The reason for this is that benign attacks are seen in approximately 2 million samples. As you can see on this figure to the right, you can see the one having 2 million samples. Those represent benign, while other attacks have less samples. This bias problem indicates that our model might only get exposed to benign attacks. So which that means that when the model sees other types of attacks, it won't be able to classify them successfully because it has not been exposed to those. And that could be a possibility. That's why we have this big problem that we need to tackle. There are many ways to tackle this problem. We decided to group attacks with similar characteristics. By doing this, we were able to go down to only 7 attacks. So we saw the attacks that had similar characteristics, and from 15 we went down to only 7 attacks. So pretty much now we have less attacks, and those attacks have more samples. As we still see class 5, which is infiltration, that only has 36 samples. But we will go ahead and tackle that problem by doing another technique that will be explained in a future slide, which will help us go to 1,000 samples for that class 5.
For the algorithms that we use in the previous mentioned data set are following: assign non-bias, random forest, logic regression, support vector machine. With the techniques, as my partner mentioned in the previous slide, we use the technique called grouping attacks, which are just group attacks by the similarity, how they are related. We use the min-max technique for two of our algorithms, and we, as he mentioned in the previous slides, we use systematic minority oversampling technique to attack the bias, the unbiased data of our data set, which is it helps with the bias of the portion of it. And finally, we use the Bayesian optimization with tree structure, which is just a better way to find the best parameters for each algorithm. Now we're gonna go to related work. In 2019, Zhang Ai and Maubat had a higher theory that mathematical algorithms could not perform as well as base tree algorithms. And they find out that performance of a base tree algorithm could potentially perform 1.8%, 3.2%, which is it's a big improvement. In the second bullet, as in 2016, Belgavik used the same dataset as we do. They use different techniques and scoring metric, but the only problem is that they use only accuracy as a measurement for the algorithms, which is it's not the best way to represent how good a model is. And finally, the third bullet, Cavello Bertoloi in 2021, he used the same four algorithms as we do, but as well, he followed the accuracy scoring, which is, as I mentioned before, it's not the best way to represent a model's performance. Now we're gonna talk a little bit about the methodology. As we can see, we divided our methodology in three portions, which it's the pre-processing one, it's labeled by the yellow square. The model training and cross-validation with our training are, and the model testing and evaluation where we compare results and evaluate our findings.
Now we're going to talk about the pre-processing part. This is a very important part when applying any machine learning technique. The first step was to combine all the files provided by the Canadian Institute of Cybersecurity. There were 8 files, so we needed to merge them together. After, we needed to make sure there's no redundant information, so we needed to remove duplicates, empty cells, infinite values, NaN values, all the information like that. After, since we're dealing with numerical algorithms, we're required to change categorical features into numbers. In this data set, the only categorical feature was a type of attack, so we changed them to numbers. So what we did is that we changed from attack benign to attack 1, and so on and so forth, so to be able to have everything in numbers. After the combination of attacks was done, which was explained in the previous slide, then we did a scaling technique to be able to scale the data for 2 algorithms, which are logistic regression and support vector machine. And then at the end, we divided the dataset into 3 different sections: training, validation, and testing, which are going to be used for different purposes during the research.
So the previous pre-processing has been done. This is where the actual algorithms are trained. First, we begin by using the default parameters, by training and testing our models with those parameters. Then we use the the Bayesian optimization, which is just gonna find the best parameter for each algorithm, and we train and test again. And once our model has been created with the best parameters, we use cross-validation to validate our results. Now the model testing and evaluation. And here's what we refit on models, which means that we're gonna fit on models with a portion of the data that hasn't been seen by the model at this point, and we're gonna evaluate our data to compare each algorithm to each other. As this is stated in the evaluation methods, we're gonna have 4 different ways, which is the confusion metrics, which curve classification report, proficiency recall curve, and receive operation characteristic curve, which they're gonna help to visualize the performance of the models. For our goal, it's to have a high recall for attacks and a high precision for our begins, which means to have the highest positive detections of attacks while having a really good precision for begin traffic.
Now we're going to talk about the results and discussion. The first way that we use to validate and see our models and how they do is by using a confusion matrix. This confusion matrix highlights the number of correct and incorrect predictions. The diagonal line going from top left to bottom right represents right predictions, while everything to the right and to the left of them represents wrong predictions. So as you can see in this picture, you can see how random forest has most of them of their values in this diagonal line. We do see every now and then some to the left and to the right, signifying wrong predictions. But when comparing it to something like super vector machine that you can see on your right, you can see that super vector machine is only detecting attacks 0 and some attacks 1, while it doesn't do a very good job at detecting other type of attacks, which signify a lot of wrong predictions and a model that is not able to predict right. In this case, by using a confusion matrix, we can see that random forest at this moment is the best model for our problem.
The classification report shows the performance of each algorithm in 4 different measurements. One being precision, which is a false positive rate recall, a false negative rate F1 score, which is a rate between 2, and recall macro, which is just ensures that every class is evaluated equally. As we can see on the left, where it's random forest, it performs really good. And if you can see in all 4 scoring metrics, we can see that we got a 1 almost in every single one. And if we see a Gaussian bias, we can only see a group 1 that it has good scores, but as mentioned before, it's just in group 1. From group 2 to 7, our model didn't detect anything, meaning that it's only detecting benign, which, as it was mentioned before, it's a big portion of the data set. And for random forest, if you look at it, it says macro average, we can see we got almost a 1, which is 0.98, which is it's really good for precision, and for call it's 0.87, and F1 score 0.81, which is really good for our model.
Now we're going to talk about the precision recall curve, which is another way of highlighting the accuracy, the scoring of a model. What a precision recall curve does is that it shows what classes keep a high precision as the recall increases. The ideal would be to have a diagonal line, horizontal line coming from the left to the right on the top, showing that as the recall is increasing, the precision is kept at the highest that it can. As you can see on the pictures to the right, you can see how random forest in picture A shows the closest to the ideal line. There is one class, once again, class 5, that does have a little of of distortion as the precision increases, the recall goes down a little bit. But if you compare it to all the other models and algorithms, you can see how random forest is the closest to the perfect model. Once again, showing that this is the best model for our problem.
The receiving operation characteristic curve, it's uh it's just another way to check the performance of a model visually by setting up the classification against the misclassification. As we can see in the figure for random forest, it shows the false positive rate against the true rate positives, which it should represent. We want to see it's of zero false positive going from left to right and having one in true positive, which is the number one on top, going all the way from left to right. That's the perfect representation of the model. If we take in account the support vector machine, it's not close to what's expected.
Now we're gonna discuss our results. As it was seen in the previous ways of showing the results, random forest shows superiority. You can also see in this image by showing the precision, recall, F1 score, and accuracy of each model. You can see how random forest is performing well above average and way better than all the other matrices. Taking into consideration the advantages and disadvantages of each model, this was predicted. Some models are not good with real world scenarios, while others are only good with binary classification. In our case, we had a real world case problem, and we were working with multi classes. There was a lot of attacks. So this is why the other three models are not predicting and doing a good job at categorizing attacks. Linear support vector machine does show the lowest and the worst results. As you can see, also, it's good to highlight the accuracy is relatively high in all of them. This is why in other papers we have seen that these models showed a good prediction just because accuracy was good. But by using these other matrices, we are able to see that they're not as good as they might think they are. To conclude, we had a problem, which was to increase that there was an increase in malicious network attacks. To be able to tackle this problem, we needed to create a model that was able to predict and categorize network attacks. We were able to create a model by using random forests, the grouping technique that we talked about, as well as synthetic minority oversampling technique to be able to create synthetic samples. And lastly, we use the Bayesian optimization with tree structure parsing estimator to be able to get the best parameters for the model. Our model shows results of 97% recall macro score. As we mentioned before, this is the best measure for a problem. The recall macro makes sure that the model is predicting harmful attacks while also taking into consideration every attack equally, no matter the size. What this also reflects is that our model is able to detect harmful attacks 97 out of 100 times. Some of the future work include working into finding feature selection, a technique to be able to find uh, the best feature for a model to be able to have less features. Also using new algorithms that would compete with random forests, and at the end, doing the actual creation of the network intrusion detection system. Thank you for your time. If you guys have any questions, please let us know. Thank you.